Understanding sklearn, Linear Model, ElasticNetCV. ElasticNetCV is a powerful tool in scikit-learn for building linear regression models with automatic selection of regularization parameters. It combines the strengths of both lasso L1 and ridge L2 regularization, offering flexibility in handling multicollinearity and feature selection. Here's a detailed breakdown of the ElasticNetCV class, covering its functionalities, parameters, attributes, and methods. Key features. Regularization. It employs a combination of L1 lasso and L2 ridge penalties to regularize the model. Coefficients. This provides a balance between feature selection L1 and shrinkage L2, making it effective for handling correlated features and preventing overfitting. Automatic alpha selection. It uses cross-validation to automatically determine the optimal values for both the regularization strength alpha and the mixing parameter L1 ratio for the ElasticNet model. This removes the need for manual hyperparameter tuning, saving time and effort. Flexibility. You can customize the range of alphas to search, the cross-validation strategy, and various other parameters to fine-tune the model's performance. Detailed parameter explanation. Let's examine each parameter in detail. 1. L1 ratio float. Default 0.5. Description. This parameter controls the balance between L1 and L2 penalties. Range 0.0 pure ridge to 1.0 pure lasso. Value interpretation. A value of 0.5 indicates an equal balance between lasso and ridge. Regularization. Closer to 1 emphasizes feature selection lasso, while closer to 0 emphasizes shrinkage ridge. Impact. The L1 ratio influences the sparsity of the model and the degree of shrinkage applied to the coefficients. 2. Apes float. Default 1e-3. Description. This parameter defines the tolerance for the optimization algorithm, determining the level of precision required during the search for the optimal alpha value. Impact. The smaller apes will result in more precise optimization but might increase computation time. 3. N alphas int. Default 100. Description. This parameter controls the number of alpha values to test during the cross-validation process. Impact. The larger n alphas increases the search space for the optimal alpha, potentially leading to a better solution but also increasing computation time. 4. Alphas array-like. Default none. Description. This parameter allows you to manually specify a list of alpha values to test instead of having the model automatically generate a range of values. Impact. This provides more control over the search process, particularly when you have prior knowledge about suitable alpha values for your problem. 5. Fit intercept bool. Default true. Description. This parameter determines whether to calculate the intercept term bias for the model. Impact. Setting this to false assumes the data passes through the origin. 6. Normalize bool. Default false. Description. This parameter controls whether to normalize the features before fitting the model. Normalization scales features to have zero mean and unit variance, potentially improving the performance of the algorithm. Impact. Normalization can be helpful when features have vastly different scales, as it prevents features with larger scales from dominating the model. 7. Precompute bool. Default false. Description. This parameter determines whether to precompute the gram matrix dot product of the feature matrix to accelerate computations, especially for large datasets. Impact. Precomputing the gram matrix can save time during the optimization process but can increase memory usage. 8. Maxiter int. Default 1000. Description. This parameter defines the maximum number of iterations allowed for the optimization algorithm. Impact: the larger maxiter allows the algorithm to explore more potential solutions but can increase computation time. 9. Toll float. Default 1e-4. Description: this parameter sets the tolerance for the stopping criterion of the optimization algorithm. Impact: the smaller toll requires a higher level of precision in the solution but might increase computation time. 10. CV int. Cross-validation generator or iterable. Default none. Description: this parameter controls the cross-validation strategy used to select the optimal alpha value. Default value none uses 5-fold cross-validation. Options. Integer specifies the number of folds for k-fold cross-validation. Cross-validation generator: custom cross-validation generator from sklearn. Model selection e.g. stratified k-fold. Iterable and iterable that yields train test splits as arrays of indices. Impact: the choice of cross-validation strategy affects the robustness and stability of the models. Selection of alpha. 11. Random state int. Random state instance or none. Default none. Description: this parameter controls the seed for the random number generator used for shuffling pay data before cross-validation, ensuring reproducible results. Impact: when you specify a random state, the cross-validation splits will be the same across multiple runs, leading to consistent results. 12. Selection str. Default cyclic. Description: this parameter controls the strategy used for selecting the next alpha value to test during the cross-validation process. Options. Cyclic cycles through the alphas in a fixed order. Random randomly selects the next alpha value. Impact: the selection strategy can affect the efficiency of the search for the optimal alpha. 13. Positive bool. Default false. Description: this parameter forces the coefficients to be non-negative. Useful when modeling positive values or relationships. Impact: enforcing positivity can restrict the model's flexibility but might be beneficial for specific applications where coefficients are expected to be positive. Attributes. After fitting the model, you gain access to several useful attributes. Core array. Shape and features. The estimated coefficients of the linear model. Intercept float, the independent term in the decision function. Knitter array. Shape n alphas. The number of iterations run by the ElasticNet solver to reach the stopping criteria for each tested alpha value. Alpha float, the selected value of alpha after cross-validation. L1 ratio float, the selected value of L1 ratio after cross-validation. Methods. ElasticNetCV provides several methods for training, prediction, and evaluation. Fit X, Y. Sample weight none fits the model to the training data X, Y with optional sample weights. Predict X predicts the output values for new data X using the fitted model. Score X, Y. Sample weight none calculates the coefficient of determination R2 of the prediction on the given data. Set params. Params sets the parameters of the estimator. Get params. Deep true gets the parameters of the estimator. Using ElasticNetCV in practice. 1. Import the necessary libraries. Python. From sklearn, linear model import ElasticNetCV. From sklearn, model selection import train test split. From sklearn, datasets import load diabetes. 2. Load and prepare the data. Python. Diabetes load diabetes. X diabetes, data. Y diabetes, target. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. 3. Instantiate the ElasticNetCV model. Python. Model ElasticNetCV CV5. Random state 42. 4. Fit the model to the training data. Python. Model. Fit xtrain. Y-train. 5. Make predictions on the test data. Python. YPRED model. Predict xtest. 6. Evaluate the model's performance. Python. From sklearn, metrics import mean squared error. MSE mean squared error retest. YPRED. printf mean squared error MSE. Advantages of using ElasticNetCV. Automatic hyperparameter tuning saves time and effort compared to manually searching for optimal hyperparameters. Regularization benefits combines the benefits of lasso feature selection and ridge shrinkage, leading to more stable and robust models. Flexibility allows customization of cross-validation strategies, range of alphas, and other parameters for fine-tuning the model. Handling multicollinearity effectively deals with correlated features, improving model interpretability and generalization. Conclusion. ElasticNetCV provides a powerful and flexible approach to building linear regression models with automatic hyperparameter tuning. Its combination of L1 and L2 regularization, coupled with efficient cross-validation, makes it a valuable tool for various regression tasks, especially when dealing with high-dimensional data or correlated features. By understanding its parameters, attributes, and methods, you can effectively use this model to achieve accurate and interpretable results.